Now remember that arrays are simply another kind of data, and as such they can be passed into or out of methods, just like any other variables. For example, recall that the standard main method interface allows us to accept external inputs as an array of strings. The important thing to keep in mind is that what's really being passed is an array reference, which points to the real data living somewhere else in memory. So when we pass client arrays into methods or return method arrays back to clients, recognize that we're potentially giving unwanted access to some other part of our program. In particular, when we're dealing with a class that's to be used as a reusable component, we want to make sure that methods such as constructors, accessors, and mutators don't inadvertently share array references to their instance variables with any outside client program. If we don't do this, we're potentially allowing some client program to have direct access to our instance variables, which would violate the principle of encapsulation. But it's important to recognize that all of the above pertains specifically to methods of some class which is intended to be used as a reusable software component in other code. If instead we have some client program that offloads some of its array manipulations to local methods for better code structuring, and those methods are self-contained within a class and not usable elsewhere, all of the above is much less of a concern. Let's take a look at some examples of both these situations. First of all, how do we use arrays as inputs and outputs of methods? Here are several examples, and in all of these, method names appear in blue, array data type declarations appear in red, and array names appear in green. To define a method interface which uses an array as an input parameter, simply specify the input array parameter as being of some array data type, using these square brackets. In this first example, this method's access specifier is public, its return type is void, the method name is setTemperatures, and this method expects as input an array of doubles called daily temps internally, followed by the body of the method. To define a method interface which returns an array as output, in similar fashion, simply specify the returned output array as again being of some array data type. So in the second example, this method's access specifier is public, it returns an array of doubles, the method name is getTemperatures, and this method expects as its input a CS12date object called date internally, followed by the body of the method. So these are how we would specify the interfaces if we were writing these methods. To use arrays as arguments when calling these methods, we just use the array name without any brackets, as seen in these first two general forms. For example, up here we saw that setTemperatures expects an array of doubles as input, so here we give it the name of an array of doubles. Up here we saw that getTemperatures took as input a CS12date object and returned an array of doubles. So here we provide it with a CS12date for today and assign the output to an array of doubles. In both these examples, we assume that both today temps and temp data are already declared elsewhere as being arrays of doubles. Here's an example which shows a situation where we really don't need to be too concerned about violating encapsulation and sharing array references, because this program is completely self-contained, and these two methods simply exist to offload some computations and aren't intended to be used outside. In this example, we're setting up two different double arrays of hourly rates and two different int arrays of employee IDs, presumably for two different stores. Notice that we're taking advantage of that special case for arrays where we can declare, instantiate, and initialize each array in a one-line initialization statement with the element values within curly braces in a comma-separated list. So what we want to do here is give everyone a blanket 10% raise. So we'll print everyone's employee ID and hourly rate before and after giving that raise. Notice that because these are repeated operations on different data sets, we've offloaded the repetitive statements into their own dedicated utility methods, which are shown down here. This first method, printWorkers, takes a title string, an integer array, and a double array as its inputs. So in each of the four calls to it in the client, we simply provide it with two array names matching the expected types, with no square brackets needed in the calls. Because we're going to be doing some computations, We also set up this format specifier to limit our display to 2 decimal accuracy. The second method, giveRays, takes a double array and a double scalar as its inputs and returns a double array as its output. But in this case, when we call it up here, notice that we're overwriting the starting rates with the returned updated rates. In other words, this method down here is modifying data back up here in the client, as also noted here. If this was intended to be a reusable software component, that would be a huge problem because we'd be violating the data encapsulation of a class. But in this context, it's really not that big of a deal because these methods exist only to support this main method client within the confines of this class. Finally, notice that each of these utility methods can operate on arrays of any size because any array parameter already knows its own size. These two data sets up here are of different lengths, but in these two for loops down here, we're simply using the generic expression for the length of any array, so any size data sets can be handled. So when all is said and done, here are the employees and their initial hourly rates. From these method calls here, we give them all that 10% raise, and then we redisplay their rates with these method calls, giving us these last two sets of output. Please take a moment now to pause this video and view the short code walkthrough for array1d method usage.java, which you'll find in the usual place. Open up this file in JGrasp so you can follow along, then come back to this video when you are finished. In direct contrast to the previous example, reusable classes are those which are destined to be used as reusable software components in the form of instantiated objects in some outside client code. In this case, we do want to be concerned with the data-safe transfer of array elements. Whenever we're passing arrays, or objects for that matter, via method calls, we always want to copy all the data back and forth internally between instance variables, so as not to violate the principle of encapsulation. So for an array, we need to do an element-by-element data transfer in a loop, and for an object, we need to do a field-by-field transfer of each instance variable. We already saw this for our person class when we talked about data-safe transfer of birth dates. For example, let's say we wanted to set some instance variable which is itself an array using a constructor or a mutator. If this orange box represents an array defined on the client side, internal to the class, we want to be sure that we safely transfer it element by element, using a for loop, to the instance variable array. Similarly, if we wanted to return an instance variable which is itself an array, using an accessor, we want to do the same thing in reverse. That is, make a safe copy, transfer the array data over to it element by element in a loop, then return the copy to the client program. By performing such data-safe transfer steps, we ensure there is no direct outside access to this instance variable, and it's kept safely private as expected. In the code on the right, here are two overloaded mutators called setData for our array class. This first one accepts some int value and appends it to the end of the array in the next available empty index and increments the count. But note that we are first checking if there is any room to add additional elements. If there is not, we simply print some predefined array full error message and nothing else happens. This second overloaded form accepts an integer array and overwrites the existing data with these new values. Like any method which accepts an array parameter should, this mutator performs the following steps. First, it resizes the data instance variable to be of the same size as the input array, which wipes out all the existing data and resets the count to that size. Then, looping over the new size of the instance variable array, it copies over the elements from the input values into the instance variable array, thereby keeping that data private and maintaining encapsulation. As we progress through all of the following examples, note that they can all be found in the example file array1dints class.java, found in the usual place. I would strongly encourage you to follow along in that file in JGrasp and view its associated code walkthrough video as needed. In this next example, in the code on the right are two overloaded accessors for our array class. This first one accepts some int index value, first checks if that index is for a valid array element, and if so, then returns the array element found at that index. Otherwise, it simply prints some predefined array index error message along with the invalid index and returns a 0 value as a placeholder, since it has to return something. In case you didn't notice, this is a different error message than for the mutator, which means we have more than one problem-specific error message defined towards the head of this file. The second overloaded form returns a copy of the entire instance variable int array. It does this by first creating a new temp array having the same size as the existing instance variable array. Then, looping over the size of the instance variable array, it copies over all the elements into the new temp array so that we can safely return that copy to the calling client, thereby keeping the instance variable array private and maintaining encapsulation. In this next example, we're checking the equality of two integer arrays. Note that this equals method has exactly the same standard interface we've seen before in our person class. We start off by assuming a true result, but then we need to perform this set of nested equality checks on the left. First, we check using instance of that the input object obj is also of the same type. If it is, we then typecast it to this object A of our array class. From this point forward, remember that the A refers to the input object and this refers to the current object we're already in. Next, now that we've determined these are both array class objects, we check that the data array lengths are the same. This multiple dot syntax might look confusing at first, but if we read it from left to right, this dot data is the int array of our current object, and we are just obtaining its length. For the input array A, we simply use one of our size methods to get its size. If these lengths are equal, then we continue checking further. Finally, in this for loop, we check element by element for equality between the array elements of the current object this versus the array elements of the input object A. Since both array elements are simple ints, we can use a simple equality or inequality operator for this. If any one element differs, our return status is set to false. Otherwise, if all three of these checks pass, then we can safely say the array objects are in fact equal. Note that we didn't compare the count variables here because checking all the array elements effectively handles that. One way or another, we return the resulting equality status as the required Boolean value. By the way, take note of the way this code is uniformly indented at each level, with each closing curly brace aligned with its opening statement. Once our program logic starts to become nested like this, you can hopefully see how these good coding conventions become more and more important. In this next example, there are a couple array utilities which add new values to our instance variable array. Suppose we want to add more data to the end of our array. Let's imagine we could obtain that data from one of three sources: user inputs from command line prompts, adding random integer values, and adding data from a file. In this code on the right, we see three alternate methods to add data to our int array. While each one gets one integer from different data sources, they all use one common setData method to handle the details of actually adding one element to the instance variable array, no matter what its source. This first version, setDataFromUser, prompts the user at the command line for a value, then adds it. The second version, setDataRandom, simply generates a random int over some range, then adds it. This is a new method you'll be adding to your utility class very soon. And this last method, though not implemented yet in this example, would read data from a file and add it to the array. Also, notice how all these methods are self-contained, by which we mean they take no inputs, return no values, but have all needed data generation or prompting internally. Finally, in this last example, here are a couple last array utilities to modify specific array element values. As before, note that each method is self-contained. It requires no inputs, it returns no value to the caller, and all the element index and value prompting is done internally. Each of these two methods is very similar. Each one uses another utility method to prompt for a valid index value. As long as there are elements in the array and the returned index is not -1, each method prompts the user for an update value or an increment value. Then, for the update element method, the specified index of the array has its value reset, whereas for the increment element method, the specified index of the array has its value incremented by the specified amount. If we wanted to decrement the value, we can simply provide a negative value. For both methods, if the index is equal to -1, that simply means there are no elements in the array, and the user is notified as such with another predefined error message constant. Again, please take a look at the example file array1dintsclass.java and its code walkthrough for more details on all these methods and to see them execute. So with this collection of all the methods we've discussed, we can implement the fairly useful and functional class centered around an array of integers with multiple methods that operate upon that array. And with that, we'll conclude this lecture video.